Our good friend Guillermo is an associate professor at TU Berlin at the Einstein Center Digital Future and the Science of Excellence Intelligence Excellence Cluster in Germany. He got his PhD from Georgia Tech in 2011, and he was a postdoc. He was a postdoc at in RPG, the Robotics and Perception Group, Davide Scaramucci's group at the University of Zurich, where he started working then with event cameras. And he's the main person behind the idea of contrast maximization, where the event cloud is rotated in space-time to line up the events. And he showed it can do motion, stereo, and even obstacle avoidance. I hope that's correct, Guillermo. Today, we'll talk about 3D DVS vision. He's also one of the main organizers of the very useful CVPR workshops on event camera vision. I've always enjoyed working with you, Guillermo, and I thank you very much for your participation today.
Thank you very much. Thanks for the nice introduction. I think it's overwhelming. Thanks very much for inviting me to present our work at this workshop. Really nice setup of speakers and the timing. So today I want to focus only on one work. I know I could use this opportunity to talk about many things, but I think I want to talk about one, and it's event-based stereo reconstruction for SLAM, and in particular doing fusing events. So the workshop is about fusion. In the past I did event and IMU fusion. Today I want to talk about two events fusion, like events from different sensors. Okay, let's see, get it going. The topic of stereo has been in our community already since the beginning. When Misha Mahal was presenting her thesis, she was building the silicon retina, but at the same time she was working on a stereo chip. And they were talking to each other. The retinas were analog, and then they were transmitting the signal digitally to the chip. So you can see depicted here, converting back to analog, and then the stereo chip will do some disparity computation. It was trying to do some bi-inspired disparity computation. And this was 1992. There is a very nice video about this from Toby, I think 2 years ago. And some recent work on this is from the people at INI, Mark Oswald and collaborators, where you can see the events will come and they will spike in both retinas, and then there will be some spike timing detector, something like coincidence detector that will try to estimate depth based on the timing of the events. And this works quite nicely for scenes with objects that are at different depths and not too many events. I would say the scenes is sufficiently sparse and there is not too many ambiguities. Depth is quite nicely estimated, although it may not be as accurate as we would need it for robot motion estimation for SLAM. You can see that the depth maps are a bit noisy here. I would say most of the stereo methods that when I was doing the literature research for the survey paper that we wrote, they tried to exploit these coincidence detectors or some coincidence constraint to say that, a spike comes to the left eye, another spike comes to the other eye, and then if these two times are sufficiently close enough and the events are in the semi-epipolar line, this is a good candidate for a match. In terms of SLAM, we know that we need a bit more geometry, we need a bit more baseline to get a more accurate depth. It's not just the timing, we need the camera to move, and this is some work that we did before with collaborators from Hong Kong University of Science and Technology. The idea is that we have two DVSs and we convert the events into time surfaces, and we design some tracking and mapping algorithms that will estimate 3D map of the scene and also the trajectory of the camera in this world. And it's a classical architecture. One worker is in charge of giving the events and the camera motion, estimate the 3D map, and the other one would be given the events and the 3D map, estimate the camera motion. They feedback on each other and they work together to solve this simultaneous localization and mapping problem. So the way it worked is that here we can see on the left the camera rig, and this is moving, and when a new event arises, perhaps on the left camera, we want to see what is kind of like the corresponding point on the right retina. And the way we did it was by maximizing spatial temporal consistency. So you want to find what is the best match on the other retina to try to, once you have these 2 points and you solve the stereo matching problem, back project and get the estimated location of the 3D point. And we want to get not only the 3D point location, but also the uncertainty about it, because next thing that we will do is that we do this different times, like 20 times per second, and we get these semi-dense depth maps, and we want to refer them all to a common time so that we can fuse them. So we do some probabilistic fusion of these semi-dense depth maps, taking into account the mean depth and the uncertainty. And this is done with some Bayesian filters with student T distributions that are adapted to the signal. So this works is like individually at every snapshot, let's say like 20 times per second, we are doing these coincidence detectors, if we would like to say, or spatiotemporal consistency, and then propagating them to a common time and fusing them. Instead, what we were trying to do is something different. We were trying to see if we could extend the monocular methods. And this is some work that we did when we were in Zurich. And when you have a single camera, there is no such thing as coincidence detection. It's very difficult to establish data association between events that are coming a long time in the same retina. So this constraint, coincidence detection, is not really exploitable here. Instead, what we did is that geometrically, you see that the camera is moving, and for every event that comes, basically we will back project these events with rays into space, and here represented with the disparity space image. And this will give you, in front of the camera, we build a ray density volume. Basically, we count in every point in space how many rays are being back projected as the camera is moving. And the maxima, local maxima of this ray density that I kind of was also presented in the talk before by Laurent, are the locations of candidate 3D points. And it is very much aligned with the idea of contrast maximization, we will see in a minute. Okay, so we have this pipeline for one camera. An example is in this one-dimensional motion with objects at different depths. If we back project the events, here these red rays represented as the back projections, and then we build this volume in front of the camera. We get the volume that is here represented on the right side. And this is a ray density volume. Light blue points means that there are many rays that are intersecting at this location. And these are the candidate locations of the 3D points. Okay, and then if we sweep along the depth planes, you will see this in focus, out of focus effect, that as you sweep the objects that are, when the things come into focus, that's when many rays are intersecting, and those are kind of like maximizing sharpness, maximizing contrast. These are the candidate locations for the 3D points. And when you estimate along each of these pixels in this disparity space image, you take what is the location of that maximum in focus point, and well, you will get what is on the right, which is this point cloud. Good.
Okay, I pause you right now. And don't worry, I paused the timer for your talk also. So this looks really nice, and it's very straightforward approach and completely sensible, but it looks extremely expensive competition because you have to maintain this big 3D volume and project the rays through the volume and then do the computations of all these densities, right? In a sliding way. You have to do it presumably in a sliding way because this is a static scene, but in reality, you'd be moving through space. So this volume is always changing. You're going to get to that?
No, but because this is, but I can reply quickly. I'm telling the story as we are shooting rays. In computing, we don't shoot rays. That's very expensive. So there is a trick to do this with homographies, and this runs in real time. On top of this algorithm, we created EBO, and this runs at 4 million pixels, 4 million events per second. So 1.1 million events per second back then in 2018. It was not too expensive.
Right, but you guys who do computer vision always say that it runs at some rate on a big, 500 watt PC, right, or GPU?
This was CPU only.
Okay, all right, well, let's see.
Okay. Anyway, the idea is that we want to get this monocular method that we know it works efficiently, right, on a CPU, and it's fast. We can do EVO, so visual odometry, moving this disparity in different time locations. How can we exploit and extend this idea to stereo? Well, easiest thing we could do is, let's do it for one camera. Let's do it for another camera. We get 2 point clouds. And now we fuse the 2 point clouds, right? The problem with that is that there will be many duplicate points. You will try to detect the same point, and then you have to do some post-processing and remove the outliers and so on and so on. This is not how we want to do it. Instead, what we propose to do in this work with Shuman Ghosh, who is also in the audience, is let's assume that we have the rays in front of the cameras, and we have in a common spatial location the disparity space image, and we have the ray density from the left camera, the ray density from the right camera, and now we fuse them. And we do like a pointwise operation to fuse them. I will get to that in a minute. And after that, we have like basically the same as before. We now have a single DSI, and we extract the local maxima and get the point cloud. Okay, this is an example of a sequence. You can see the events on the left and on the right. Monitor scene recorded in Zurich. On the left, you see the individual DSIs. On the right, we see the fused DSI. So these ray densities. It's hard to see the difference here. We will see it better with a 1D example. And as you sweep along these planes, you will see that the number of events come into focus at the correct location, right? This is the in focus, out of focus effect. And detecting local maxima will give you the depth map, and the confidence map is really nothing more than how many events happened at that maximum point. Black means many events intersected there. White means very few events. With a one-dimensional example, we are moving here the cameras sideways with a front to parallel scene. And you can see as you sweep through these depth planes that the rays intersect at the correct depth location. On the right, see the side view. And the point cloud also looks quite planar. So if we compare what is going on, how can we merge the ray densities, and we can compare the monocular and the stereo one, we see that even when the camera has moved very little, like 50 milliseconds, these three images or projections that we show is the front projection, the top view projection, and the side view projection of this 3D volume. In the monocular case, we can see the shape of the rays. We can see how we have been shooting them from in front of the scene. In the stereo case, fusing with the harmonic mean, I will come to that in a minute, is very, very different, because if you look at the side view or the top view, we see that there are two sets of rays. The rays coming from the left camera and the rays coming from the right camera, which here are curved because we are using an inverse depth parametrization. But you can see already here in this boundary or in the other one that there is not just one set of rays like on the top image, but two. And you know how these agree on a measurement, they will give you a much highlighted structure. If we increase the amount of time that happened, like 200 milliseconds, you can see that the localization is improving in the monocular one. So these rays are becoming more constrained. We are starting to see the location of the plane, but in the stereo case, we're almost there already. The same if you look at the scene and the side view, the localization, so the convergence to the structure is much faster in the stereo case because you have the rays and you fuse the rays in a very sensible manner. And after 1 second, it's settled, but the stereo is still quite better. So to fuse them, we tried many different functions, and the generalized means work quite nicely. So the generalized means are the power means also. They go from the minimum to the maximum, and you have the harmonic mean, geometric mean, arithmetic mean, quadratic mean. This basically says how do you fuse the number of events that are on the left image and the number of events that are on the right image at the corresponding voxel location in the disparity space image. And the arithmetic mean would be just summing the number of events, the number of rays that intersected, and it's good enough, but it still suffers from outliers. Instead, if you use the minimum or the harmonic mean, you are saying that the values will be high only when both the count of events on the right image and the count of events on the left image, when both are high. It's kind of like an and condition, a very simplified way to look at it. And this works much better because it removes these outliers. So we compare with the state of the art, which is the generalized time stereo. semi-global matching adapted to events and ESVO, and we can see that the results are kind of thinner edges, well spread over the image. We tested it on 3 different resolutions. So let me show you examples on MPSEC dataset. So we compare, on the left is the monocular one, on the right is the stereo one, and in the middle is the ground truth and ESVO, and we get kind of sharp 3D edges. We are also able to recover structure in places where there is no ground truth. This is like a nice example to show that it can get denser depth maps than ESVO.
Yeah, that looks really nice.
This is a complicated example. We have when the motion is on a drone and it's moving back and forth, it's kind of a difficult motion for 3D reconstruction. It's much better if we move sideways than if we move forward and backward. Anyway, it's also good to filter out outliers, as you will see in comparing the monocular and the stereo one when you get to the carpet in a minute.
And the confidence map here is simply the value of this harmonic mean averaged over time, or for the very last frame?
Is the maximum on the DSI. And
okay.
we get, like, I think here for, depending on the data set, we collect different number of events. This is results on the DSEC dataset. Matthias is in the audience. He collected this data and put in 2 cameras on a car. And you can see that we get nice depth results even when there is no ground truth from the LiDAR, nice depth maps. And now when we get to the accuracy, it's better than the monocular one, the ESVO, and it also filters out the outliers. So this is VGA resolution, generation 3 prophecy, I believe. The previous one was the Mini Davis 346. And we also have results on this dataset, 1 megapixel camera from Prophecy, dataset recorded in TU Munich. As you saw, cameras on a helmet. This is in a motion capture room, so the poses are given by the motion capture system. Well, we still get nice depth maps. Outside the motion capture room, we use the poses computed from the frame-based camera just for the experiment. You see, this is forward motion. It's really difficult. There are many events here on the top left, but only a few of them we can really get good depth estimates. Outdoors, it's also quite well, and you can see the depth maps are really quite impressive. I would say densely populated, many events in these 1 megapixel cameras. Okay, so running out of time, but a really interesting question that we had was, all the previous stereo methods were using this event coincidence. Do we need event coincidence to do stereo for SLAM? Do we need to, look for matches that are close in time? And this result really was blowing our minds. Imagine that we do this, we back project the events, we get these disparity space volumes, and we can do it for 2 subintervals. And we do it for the left camera, for the right camera, and now we say, okay, let's match the first subinterval in the left with the first in the right, the second in the left with the second in the right. We get now 2 DSIs, which we can still fuse to get another one and extract local maxima. And these are the results that you will get. Okay. Now, what happens when we shuffle the subintervals? The results are not too different. I mean, we see a decrease of the field of view. You can see the overlap that it's smaller, but it's quite amazing that these are events from completely different subintervals, but the depth estimates are almost as good as when they were from the same interval. And yeah, I guess the idea here is that we are using the knowledge of the poses to refer the events to another representation, which is convenient for depth estimation for SLAM.
But are you accounting for the time delay between those estimates? Because there's motion stereo, right? Motion is equivalent to stereo disparity. If the camera is moving laterally, then of course the time that you choose, it has to be correct. Otherwise you get the wrong triangular estimate of the disparity, right?
So all the things that these have in common is that we are counting the events in a single DSI in space. So all of these DSIs are counting events in the same region in space. Sometimes we count it from the previous interval, sometimes we count them from the next interval, but we know that they are all counted in the same 3D region in space.
Okay.
And even we extend it in and show that you can scale linearly with the number of cameras. This is, I guess, will be presented by Cornelia, this data set that they have at the University of Maryland with synchronized cameras. And we show, yeah, some depth estimation results. You don't need to compare pairwise. You just need to put all the events into these DSIs and fuse them linearly in the number of cameras. Okay, so to conclude, the stereo problem, I mean, for us was very interesting because it poses this fundamental question about event matching for 3D reconstruction. And we found that, you know, establishing event correspondences is not needed in stereo reconstruction for SLAM. We kind of knew this for monocular case, but now we also know for the stereo. And more importantly, for stereo event coincidence, or trying to exploit this constraint that you need to match events because they have the same or very similar timestamp, this is not needed at all. But again, we have something additional, which are the camera poses. DSI fusion produces state-of-the-art results. As I tried to show, the stereo improves the speed of convergence to the 3D map, removes outliers, and it works across different resolutions. I'll show examples on 3 datasets. It scales linearly with a number of cameras. This is in the EBMO dataset, and code is available. We are just waiting for the license. These are some references. The paper that I presented is here, and the one on the top, and there is the research page from my lab. I have some videos that I built for a course at TU Berlin, a paper that Toby and I and more collaborators wrote together on the review of the topic, and the list of event-based vision resources where we try to put many of the literature, workshops, and things that are going on for people to quickly access them. Thank you very much. Open to questions.
Yeah, by the way, I just want to say thanks for that lovely talk. It's quite clear. Also, Guillermo is the driving force behind this lovely GitHub site, this event-based vision for resources. If you guys in the audience don't know about this, this is the place where if you have a paper related to this entire field, it needs to be listed. And you just submit a poll to Guillermo, and he makes sure that everything's right with that. Thank you for doing that, Guillermo. And then it's there forever. I mean, it's really great, Guillermo, that you're maintaining that.
Thank you.
So yeah, I'm happy for some questions here from the audience. Otherwise, I'll ask my question about computational efficiency. I really like this because you're getting away from, this is all handcrafted. There's no DNNs here, right?
No.
It's all handcrafted, like just using human intelligence, not artificial intelligence. But I do always care about computation, right? And now when you're trying to do stereo vision for robotics, it has to be in real time, right? On a limited power budget. So yes. Just tell us, if you don't mind, some of the tricks here to do that. You mentioned there was a trick, but you didn't really describe it. To do, instead of projecting rays, yeah. Or is it too much to ask that?
Well, the trick is that you back project the events to the first depth plane, and that's expensive. It's a homography. But after that, projecting the events to many other depth planes is cheaper because it's not a general homography, it's a similarity.
But does that mean that means you have to go and write a bunch of memory which represents those different planes, right?
Yes, but you can vote for you can do this in parallel because every depth plane can be treated independently. Okay, but you need to maintain a memory which is basically the number of pixels times the number of depth planes that you care about. And those depth planes are presumably are not spaced uniformly. They're spaced in a way that represents, you know, the resolution that you have, right? Or are they spaced uniformly? They are different ways to do that. You can space them uniformly in depth or in inverse depth. It actually works better for large scenes in inverse depth. And now you have this large memory structure. I mean, I call it large, right? And in terms of hardware, it's large, right? Because it's really a 3D volume of depth. And now what do you do for a moving camera that's navigating through space? How do you maintain now this depth map for a robot that's driving, for instance? You don't keep like a continuous version of that. It's not like the one that it's continuously updated. You just keep at different reference viewpoints along the camera trajectory. So here it's represented with this And I mean, at some point along the camera trajectory, you decide on a point where you're going to build this, and then 2 seconds later or 1 second later, you build another one.
So you keep that one, maybe use it for a while until you know it's obsolete, until you're not looking there anymore?
Yes, I mean,
okay.
I'm not sure for.
Have you ever closed the loop on anything robotic with this approach for navigation, or use it for?
Yep, let me try to show the monocular system that we have. The stereo, we are still working on it, but I can show the monocular one, and it's. Can I share now again? So this is the monocular one. It's a EVO, right? This is building the DSIs and doing the tracking. And this runs in real time, and the code is available also. So with the stereo, the only thing is that now you have 2 DSIs. So you will be able to process half of them. As you can see here, Timo is moving the camera. We are recording, and we are comparing the ground truth pose with the estimated pose. And the DSIs are being built. We don't see where exactly, but we see that the point cloud is being back projected and refer to create this global big map of the scene.
Okay, so you have a big memory that's the global heat map, and you're filling it in a little bit like Shichi showed, right, with this thing, but filling it in as you get more information.
Yes, we have several of these disparity space images, which are local maps, and then when we back project and merge, fuse them all like a big map, this is what we see on the top left.
I see. Cool, thank you.
Yeah.
Anybody raise their hand? Yeah, please.
Hi, Guillermo. Yeah, actually, the talk is very interesting. So at the beginning, you said there are 2 kinds of methods for fusion, like early fusion, and so I want to know, because you did the early fusion. So can you comment like what's the difference if you do it at last? Is the performance work, or I mean, is there some comparison?
Yes, I mean, maybe it'll take time to find the images, but we did this approach where we fuse the point clouds and we observe, like, you know, duplicate edges and sometimes more noise. It's really not ideal to do the fusion towards the end. We think it's much better, and we actually computed it with numbers. I think you can ask Schumann to do it earlier, to do it at the DSI level rather than at the point cloud level.
So it's because of the accuracy is worse, or because of like computation cost or something like that?
That's accuracy. I mean, in the end, you are to compute the depth and the confidence, the depth map, you are thresholding, right? There is somewhere here that is this adaptive Gaussian thresholded that you are going to say this point has a good depth estimate, and then you will back project it. But this thresholding is kind of not ideal. It's very nonlinear. It's better to fuse earlier on, before the thresholding.
Okay, thanks.
Really nice talk, Guillermo. Thank you.